Right. Hello, everyone. My name is Andrew Blackman, and it's my pleasure to introduce this webinar. It's been arranged as a joint venture between Survey and Spatial New Zealand's Positioning and Measurement stream and its cadastral stream. NZVD2016 was released as our new national datum almost 8 years ago now, in July 2016. Prior to this, we had to rely on a mixture of local vertical datums that had been established by precise levelling, such as Auckland 1946. They were isolated from each other and were in terms of local tide gauges that had been established at different moments in time. Precise levelling is highly intensive, labour intensive, and with the mountainous nature of our country and our limited resources, creating a national network by this means was probably never going to be possible. Therefore, a national datum based on a geoid model rather than a single point is a great step forward. This national network is maintained by a monitored GNSS network. For quite a while, local authorities were slow to convert, but recent progress has been good, and now just over 50% of local authorities require levels in terms of NZVD 2016. Late last year, the Surveyor General announced it would be compulsory to use NZVD 2016 in all cadastral survey data sets from the 1st of July 2024. It is anticipated this requirement will encourage the remaining local authorities to follow suit. To avoid confusion, a change for cadastral purposes will ideally be accompanied by a change for other purposes, such as resource consent, engineering, and other construction work. Firstly, to set the scene, we will hear from Rochelle Winefield, who is the leader of the Datums team in LINZ's geodetic section. Rochelle will discuss NZVD 2016 datum in general terms and provide additional information about transformation grids. Next, we'll have Carl Walton, a cadastral surveyor in LINZ's plan approval section. He will outline what effect the rule change has on compliance with the survey rules after July the 1st. He will also discuss some aspects of re-establishing height-limited boundaries when mark levels have changed or marks have gone. Following this, Dave Stewart, a surveyor in private practice, will discuss the methods for establishing and transferring NZVD 2016 levels. This will remind us of some good survey practice, the importance of metadata, and some things to consider with datum conversions. We will conclude with a panel discussion where we will put questions to our three presenters. We have a number of pre-prepared questions, and there will be an opportunity for questions from all of you that are watching through the Slido app. Also, perhaps we'll ask for questions at the end of SL. If any questions come through while a speaker is speaking, I might ask a couple of questions just after each one's finished. Right, so to start, let me introduce Rochelle Winefield. Rochelle has a BServ from Otago University, and she gained an interest in geodesy working on deformation modelling as a summer project. She started at LINZ in 2007 and completed a Master's in Geophysics while collecting data and developing NZVD 2016. Rochelle has been leading the uptake of NZVD 2016 over the past 8 years, as well as working on and leading other aspects of data management in New Zealand. So over to you, Rochelle.
Cool, thank you very much, Andrew, and thank you for organising the event today. I'm sure that this is a great time to have a bit of a recap of what is happening in the vertical datum space. So, as Andrew said, we've heard about NZVD 2016, and most of us have worked with it over the last eight years. So I'm not going to go back to basics, but just give a bit of an overview of what is happening in the vertical datum space. So when you think about vertical datums in New Zealand, there's basically two different types that we use. There are orthometric heights, and that is our local vertical datums, like we've said, Auckland 1946, but also many other vertical datums that we know are in use around the country, such as the city datums that are used in central cities. There's also New Zealand Vertical Datum 2016. So this is an orthometric height system, just like our levelling datums, and can do basically all of the same things. The third type of vertical datum we have is the ellipsoidal heights, and this is the ones that we use when we interact with Geodetic Datum 2000, and these are quite different to the orthometric heights. One of the things just to bear in mind here is none of those two different types of height systems that we've mentioned there, or the datums, are mean sea level datums. And here is an example from Auckland, which are going to be used throughout my presentation today, where you see the current mean sea level in Auckland Harbour is about 1.75 above Auckland datum and 1.76 below NZVD 2016. So, and that will change over time. So, while we can draw a comparison between those datums, they are not the same thing and should not be considered as a mean sea level datum. So, putting this in a bit of a diagram form, what we're actually looking at is we've been quite used to having an ellipsoid-based datum, NZGD2000 in its ellipsoidal heights. And we know that that's quite a nice curve that sort of goes around the world that the GPS system's quite happy with. When we think of a geoid, it's also a really nice surface that sort of goes around the world. It has a few little lumps and bumps on it, but it's pretty much static, just as that ellipsoidal surface. When we come to our oceans, and if we were to let them flow through the continents, that would pretty much be what our geoid surface is. The surface that changes in this scenario is that Earth surface, and that changes over time, up, down, and sideways with deformation and other types of events such as geothermal activity, which will change that. But what we're really happy with here is that that geoid surface and the ellipsoidal surface will remain static over that time. So if NZVD 2016 and our levelling datums are both orthometric datums, what are the differences between them? And the major difference is all about improving the definition. And when you think about how the datums have been established, we're going back to our levelling datums where there was a tide gauge put in the water. It was observed for a period of several years. And from that, we determined a height which was referenced to a benchmark. And that benchmark then became the truth for that datum. And then that got levelled out. And to check a height, you really need to go back to that reference mark. For NZVD 2016, we have a surface, and so that means that wherever you are across the country, you're able to connect to that surface without having to go back to a single point. When we are looking at our levelling networks, we know that they're really long, poorly constrained networks. They can go for many, many hundreds of kilometres without tying back. So any errors in that network can propagate pretty quickly. We also find that when we're coming to levelling observations, we're only testing accuracy between marks which have actually been observed. So that if you have a levelling loop that doesn't close and another levelling loop that doesn't close and you connect between them, there's actually no way of determining what the accuracy between those marks are. So when you look at a first order Auckland 1946 mark, we have determined its order about its observational accuracy, not how it connects within that network. We also find that benchmarks move, and there's actually no way of easily determining whether a benchmark's moved, apart from going out and redoing all of that levelling again. And with things like traffic management regulations and the fact that it's quite cost intensive, that hasn't been repeated. And also back on that reference to mean sea level, when you see this little chart here, you sort of see that Auckland 1946 was measured between 1909 and 1923, so that's a period of 14 years in the distant past. You need about 18 to 19 years to actually have a full tidal reading to be able to get a really accurate sea level reading. And you can sort of see that that was quite a long time ago for us to be basing our measurements off. So it's really good just again to keep under your head that even if you are working in 1946, that is not a representation of a current mean sea level. And then when we look at how the geoid's been created, it's quite a different beast. We've been able to determine it using gravity data observations. So we've taken historical gravity data from our ship track surveys, from our terrestrial surveys, and then a gravity flying campaign that took place in about 2014 to be able to determine that surface across the country in quite a regular pattern. And what that means is that any time that you take a GPS reading anywhere on the Earth's surface, you can measure that ellipsoidal value, you can calculate the difference between that and the geoid value, and you can determine an NZVD 2016 height wherever you are. The really neat thing about this is that you can also level. If you have 2 marks in terms of NZVD 2016, you're also able to level between those marks, and you will be able to get the accuracy as stated on those survey marks. So it can be used with both of those methods. One of the limitations of our levelling networks, as I said, they're really long spindly networks. And here's an example from the Auckland region where you see the marks the survey network has gone through. And when we've put that into our NZVD 2016 database, we're able to connect all of our GPS observations along with that levelling observation. So we're able to constrain the heights of our GPS marks to those levelling observations. And what this means is we're able to provide NZVD 2016 to a greater degree of certainty in these more rural areas or away from those state highways. And it also means that no matter which one of those marks that you use, you'll find that they're in terms with NZVD 2016. Another question that comes up quite a lot is about the vertical datum relationship grids. And it's really important to note that these were a snapshot in time. And the purpose of them is to allow people to convert from those local vertical datums to NZVD 2016. They are not a long-term tool, and there are errors and uncertainties in them, but they're there for a purpose to get people who have data over large areas to be able to do a quick conversion. A very similar approach was taken when we moved from NZGD49 to 2000. If you look up on the LINZ website now, you can find transformation grids that were created during the early 2000s to allow for that, but you wouldn't want to use those today due to the secular deformation and localized events such as earthquakes that have occurred since then. So it is just a tool to help people in that transition period. And as the other speakers will talk about today, you can use other methods to convert between the datums when higher degrees of reliability are required and you're looking at a much smaller area. So how these grids were created was that we looked in the geodetic database to see how far our levelling networks extended and where we had data in terms of an individual datum. So again, I said I'd be using Auckland for example, and you can sort of see that it extends quite a large way. It's also really interesting in this image that if you look up on the Coromandel Peninsula, we've managed to get some Motoriki marks up on the peninsula, which obviously haven't been connected to the Motoriki datum. And this is just a really good example about how people have assumed the datum in an area to be one of the local datums, and it sort of propagated itself around bays which have never been connected and adjusted into a levelling network. So there wouldn't be a great deal of confidence that that levelling there would actually match up with the Motoriki datum and provide a really good connected result. So we took that data and then we looked at the points where we had both levelling and GPS observations in terms of the local datum, and these are the control points that we use to create the grids. And we actually use Snap to create these grids, and this is what they look like in their raw format. So they're a 2-minute spacing grid about 3.5 kilometres. And when you look at the values of the grid, you sort of see it has a mean value of about 2.9. And if we'd taken the same approach to what we did with vertical datum 2009, which we had for a little while there, this would be the offset value that we would have determined for that for the grid. So it gives us a little bit more accuracy, but it's still just a model that of best fit to help us with those the transformation. And once you've got those grids, the method that you need to use before you apply them is bilinear interpolation. And by using bilinear interpolation, this is the model at a much larger degree of granularity that you can use to calculate the heights in an area. So you can't really use this grid to calculate the heights, but once you bilinear interpolate it, this is what gets used, and this is what's been used in the online coordinate converter to provide the connection between the models. And what you can sort of see here is that when you take the data that we've got captured in terms of NZVD 2016, and you take the Auckland 46 data and you convert that to NZVD 2016, and you can see the differences. This is what the differences that we're actually getting with the model, and you can sort of see that on those leveling networks that we had along the major highways, we're getting about plus or minus 2 centimetres, but there are areas where there are marks much greater than that, and if you look in the Auckland central area, you can sort of see that they sort of propagate all around the place, but that's really just the limitation of the data that we have, and it really sort of underlies how much uncertainty there is in that Auckland 1946. So when there was that question, is like, why do we need to move from Auckland 46? Because we don't see many problems with it. Diagrams like this sort of show how there are some underlying uncertainties in that data that is probably just going to get worse over time. And so what that means for you is that when you go into the geodetic database and you see that there is a mark which has a vertical datum height and a Auckland 1946 height, and you take that ellipsoidal height and you put it through the online converter, that you might find that the converted height doesn't match what's in the geodetic database. And that's because the information in the geodetic database is from observational data which has been published. Well, this information that you've calculated has been using that model, which really shows the difference between the two methods. And then it's up to you and some of the information that will be discussed later today to determine which one of those approaches is most relevant for the area that you're working in. And that was the end of my presentation there today, Andrew.
Hi there. Well, at the moment we don't have any questions that have come through for Rochelle, but so we'll jump to our next speaker. But perhaps what we'll do is, if there are any questions that are relevant, we will ask those at the in the panel discussion stage at the end.
Sounds great to me. Thank you, Andrew.
Right. Oh, well, we are having a few technical problems, but I will try and introduce our next speaker, and hopefully we can actually bring him to you. So our next speaker is Carl Wilton, who is a licensed cadastral surveyor who spent 20 years working in private practice before moving to Linz 7 years ago, where he works with Mike Morris and his team in property rights. Cadastral surveying has always been a passion of Carl's, and he's currently the chair of the cadastral stream for Survey and Spatial New Zealand. So we'll try and see whether you can hear from Carl. Take it away, Carl. By the look of that, I think Carl will not be joining us at the moment. So in that case, we will jump to our next speaker. So our next speaker is David Stewart, who is a Taupo-based engineering surveyor with over 30 years of experience. He is currently a director of Energy Surveys, a company that specialises in precise monitoring surveys. David has extensive experience leading survey teams on large infrastructure construction projects, but he has also had roles with traditional consultancy firms. His company regularly provides clients and peers with best practice advice on the implementation of the New Zealand geodetic system, including NZVD2016 and its associated geomodel. So perhaps we can jump to David.
Hi everyone. I'm just running off a Google Run sheet, which I need to remember to share first. Right, you should be able to see my screen now. Jenny, you interrupt me if you can't. My job is to explain how you might obtain a NZVD 2016 level for your survey. Obviously, there's a range of methods you could use: levelling, using a robotic title station, RTK GPS, static GPS, static into positions PP. There's some pros and cons of all those methods, and it's like everything we do with surveying, it's horses for courses. And this is not considering what you might use as your origin just yet. We'll get to that later. But by levelling, you could achieve a high level of accuracy, as Rochelle said before, but it's fairly time and resource intensive. But then again, if you are revisiting a site regularly, then that is going to still be beneficial to provide the best relative accuracy that you can have around your particular site, or even an area where you regularly undertake work. Over time you can build up your own control network, which is, you've got more confidence in than maybe just pulling marks out from the geodetic database for each survey. You can use a robotic title station for levelling, maybe not just using prisms on tripods. You can eliminate some air resources by having a pole with a fixed height. A few things to keep an eye on there, but we'll touch on that later too. RTK GPS, that allows you to bring in control from a bit further away, but obviously you don't have great accuracy there, and certainly not with a single determination. So multiple determinations will help you a little bit there, but especially with some time separation, not just measure and then measure again. Static, that allows you to increase the range to however long you need to, but you'll need more than one receiver, the time can start to build up as well, especially if you're covering large distances and you need to be doing recce and finding marks at the same time and that sort of thing. And the occupation length increases the longer the baseline that you wanted to measure, and you're going to need some post-processing software, which maybe not everyone has. One of the benefits of static as a method is that most equipment types allow you to log static data at a GPS base while you're also undertaking an RTK GPS survey. So you might, for example, be turning up at a site, setting up your base station, going to do a topo, some set out, whatever, and you're there for most of the day, and at the same time you're logging static data at your base, which you can then post-process relative to something else later. If you've only got your one set of gear, then that's not going to be hugely helpful, but you can also obtain static data from third-party cores, for example, GeoNet, which has, depending on where you are, you might have all these stations which you can utilize in your network adjustment, process baselines relative to them. You may not want to hold them fixed, but they might still strengthen your network. Similarly, you can request or purchase static data from a commercial GNS correction service provider. For example, the three ones which are commonly available around New Zealand, and you can build up all these types of data into a single network, like I mentioned before. What I'm going to do now, though, is show you how you can use Positions post-processing service to upload some data and get a solution out of that. So there's some reference information on that page. We will be sharing this run sheet with all these links, so you can refer to it later if you want to. Down the bottom there's some guidance on expected accuracy by the method. Which gives you some guidance on occupation, length of time, accuracies that you might achieve by the method and such. To input the data, you need a RINEX file. So RINEX is not the default format logged on most equipment, but it should be supported on all equipment, and often it comes as a free software tool from the manufacturer to convert the native format to RINEX. So you've got your RINEX file. All you need is an email address. I'll bang one in. You need to upload your file. So RINEX file looks something like that. The 17, I think that means the data was collected in 2017, and the O is the observation. You'll see with RINEX there's also with that particular survey there would be a 17N and a 17G, I think, which is almanac stuff, which we don't need. Click next, upload it. Right, so the Positions PP post-processing service needs to know what antenna type that you have. So that's selected the Leica GS15 there because that was in the data. There's other ones there available on the list, but you do need your receiver to be on that list to use the service. So you probably want to check that out before you go and do your survey, because if it's not there, you won't be able to use this method. Hit next, and you'll receive an email. Maybe you need to check your junk folder. Mine seemed to go to my junk folder for some reason. And about 10 minutes later, you'll get some results. So it'll come back. I did this yesterday, so this is what comes out of there. It gives you a report. There's your height, NZVD2016. It's giving you some error stats and how it fits the error stats there to the cause site that it calculated it relative to. And then these files that you can download, I normally just download the zip and then deal with it from there. So from that download file, you'll get a KML which shows you how it's been computed. So in this case, it's a site down on the side of the desert road, off the desert road, no good quality benchmarks conveniently nearby, although there are some a few kilometres away, but yeah, and it's calculated a solution relative to the lens cause stations, which it's a pretty simple exercise to establish a reliable coordinate and NZVD 2016 height at a site where you really don't have many other options. So yeah, it's a good way to get started. You're probably not going to do a second setup and establish another one by the same method and then hang surveys off each one. You're more likely to use this as a method of establishing it and then an origin to start from to do whatever other survey you want to do. So I talked before about how you can actually be a bit more complex about how you do it. So for example, if you're establishing control for a site where you need a high level of precision, and accuracy, you might do something like in this example where we've brought in GPS as a framework. In this case, it's static, but there's no reason that couldn't also be RTK if you've got repeat observations and plenty of redundancy as a reference framework. Some total station control to tighten up the network internally, mainly for horizontally, but taking care with measuring heights of instruments and targets, then that can be used too. And obviously some precise leveling to really improve things. So in this particular case, the best control mark in that area was round about here. There was another lens mark there and another one down here. And yeah, so this sort of is a combined option to bring levels into the site, checking against other reference benchmarks at the same time. In this case, making use of a global survey core site, not to hold it as fixed as a coordinate origin or level origin, but just to provide some additional network redundancy. And then a more complex example. Again, if you're going to be working in the same area a lot, it might be, like in this case, a subdivision, but even if you just operate in the same neighbourhood regularly, there's benefits from combining observational data into a least squares adjustment. It might be Snap, it might be whatever software you might have that comes with the equipment that allows you to combine GPS leveling, total station observations into a 3D least squares adjustment. And that then means that you've got a high quality of control, which is probably of far greater density than what you can get out of the Lens database, but also because you did it yourself and you've got your least squares adjustment with all your accuracy stats on it, you can probably have very good confidence in the quality of your data, and you know whether there's anything that you might need to go and double check or observe some more observations to improve it further. So that's how we might survey to establish an NZVD2016 height, but obviously you need to start with an origin value of some sort. So with the geodetic database, most marks, well, that was a bad example. Most marks will have a height in terms of a local vertical datum and and NZVD2016. So go and find the one I was actually meaning to look at. Right. So here you've got NZVD2016 3V and Matariki vertical datum 1V, and you might think, oh, well, 1V, that's better than 3V, so I should use that and convert it. But actually, if we want VD16 heights, we should be starting from this value, knowing that 3V has pretty much been assigned to anything that's got a 1 to 5 NZGD horizontal order. So if it's 1 to 5 up here, you should have at least a 3V NZVD2016 there. So if we go to the database and we look at these 1, 2, 3, 4, 5, and we zoom in on pretty much any town in New Zealand, you'll find that you've got pretty good coverage really as a starting point for NZVD16. However, in the data, in the database, there might be some clues as to why you may not want to use that 3V level as your origin. In this case, that's clearly in the geothermal area. You might look in there and see that over a shorter period of time, that value has been revised, and not just by small amounts. So in this case, you're probably better to choose a different origin value. Just also be aware that when you're transferring in using whatever method, if you've started from, say, on one day, you've done a survey that started here as your level origin, you checked on this mark and you transferred to here, and then a year later, you've started from this benchmark here, you've checked on that one and transferred to here, you might find that when you connect them, you're struggling to achieve the nominal accuracy of these two marks, because you've maybe introduced errors by your survey method of coming into there, and you've shortened the distance between them. So, which comes back to the tiers of accuracy, which in there. So some more information about heights and orders here, coordinate orders, height orders. That's your 3V there. Basically 20 mils plus a range component. Maybe we can ask Rochelle to explain a little bit more later as to what that actually means. So I described some pros and cons about GPS methods up there. I won't go into detail. You can have a look at that later if you want. Obviously, if you're going to choose a LINS benchmark as your reference level, you do need to check onto something. Checking onto another mark of also the same order would be a sensible step. And yeah, there's lots of different ways that it might be practical to do that depending on your job site. Obviously, with all these options of how you go about your survey, what datum are you actually doing it in at the moment? There's lots of agencies that still require data, not in terms of NZVD2016. So it's conceivable that for some jobs, you might be needing to manage duplicate data sets in terms of multiple datums. And so you're going to need to have good documentation as to, what is your data in terms of, what is its origin, how did you get there? Especially when you've got multiple data sets, because the difference between the two datums is not much. As Rochelle said before, with Auckland vertical datum 46 and NZVD 2016, that was 0.34 or something similar to that. So at a glance, unless you're really familiar with the data set, you're probably not going to be able to distinguish from the level itself which datum it's in terms of. So in the LINS database, there's always, what is the order in terms of NZVD2000? What is the order in terms of the height datums? What is the authorization date or the calculation date? What are there any important notes associated with them? And I would suggest that it's good practice to record all that information within your own data set, so you've got a good record of, what was my origin? Where did I get those values from? have they changed since I extracted those values from the database? Obviously, with transferring height by whatever method, if you choose to use a pole, if that same pole is being used for lots of topo and set out and it's been repeatedly ground into the ground, you might be surprised to know how much may have worn off it. It's a 2 metre pole can end up being 1.98. So that may not matter if you're using a fixed pole and always using the same pole, but if you start to mix and match instrument heights and target heights on tripods, and your pole height's not right, then you're going to straight away be using up or introducing errors into your data set. What is the type of mark itself? If you've got an iron tube type mark and you put your pole in it, your pole's probably disappeared up to 50 mils inside your tube. So that's maybe not a great type of mark to be using for leveling by that method, and maybe a rod or something is more appropriate. Even benchmark plaques or those kind of marks can have a central depression in the mark that your pole will disappear a couple of mils inside it. It might seem that a couple of mils doesn't matter, but you know, if you want to be accurate, then you need to account for that. It might mean that you put a different shoe on the end of your pole, especially if you're only interested in levels. GPS suitability. If you're pushing the envelope with occupations next to trees and buildings, you might get an answer, you might get a result, but will it be meeting your accuracy requirements? Redundancy, especially with RTK GPS, but good practice for any type of data. Allows you to have greater confidence in your results. And if you're out there doing 2D surveys 3 days a week and you need to do a 3D survey on the other days, then maybe you don't have default habits which help. I mean, I know a lot of 2D surveys are done with an instrument height of 0 or 1.5. So, you know, you can train yourself to, well, why not just put in the correct instrument height? How much time does that cost you? And you develop good habits so it's there when you need it. So to convert existing data sets to NZVD 2016, for most surveys, which are relatively small areas, you should be able to just determine an NZVD 2016 height for one of the marks in your data set, and then just apply a constant Z shift to your data, especially if it's by terrestrial data, so leveling or total station observations. If it's a RTK GPS data set and you have used the geoid, the correct geoid to start with, even if you're in terms of not the NZVD 2016 datum, then you should at least be parallel with it. Maybe it's a little bit more complicated if you've used one of the relationship grids, but if you just use the pure NZGeoid 2016 datum in terms of, NZGeoid 2016 geoid in terms of whatever datum, then your data should be parallel to NZVD 2016, and you should be able to just translate by a constant Z offset to shift that data set. Obviously, prudent to do some checks and have some good metadata recorded about what you've done, especially if you've done it in CAD. you know, CAD's got lots of tools, but doesn't leave much of a trace of what you've done, especially if you're overwriting the data. So I want to consider copying the data, appending the layer name with a suffix that says, you know, converted by what, put some text into the layer, just something to leave a trace, some file notes, whatever. With the geoorder itself, it's worth remembering, well, what exactly is the geoorder? And it's, you know, it's basically a series of points with an interpolated model between them. So you're really not going to find an anomaly within that scale, because it's just an interpolation between 4 points. Well, I can go into some more detailed examples, but we'll just see if we've got Carl back. Ooh.
Unfortunately, we're still having issues with Carl's internet.
Do you want me to carry on, or do we want to deal with some questions, or what?
Hi, we have got quite a few questions come through, Dave, both for you and Rochelle, so we could jump into those. One thing that, you know, we've tried in the background to get Carl up and going, and it's not working. So what we'll do is after this is we'll get his presentation and email it around to all the attendees so they can at least have the sort of written presentation to have a look at. It's just a little bit unfortunate. So, but perhaps we could bring Rochelle back maybe at this stage, and we could have a look at some of the questions. I'm just sorry, I'm just going through trying to find some of these okay, righty ho, I've got one here. It says, given relationship grids are time sensitive, can that be stressed on Linds's published information to help force local authorities to move to NZVD2016? Not totally sure what that.
So that was when I mentioned that the relationship between the datums will change and the grids will deteriorate over time. And there's a couple of little points on that. First of all, we can't force the local authorities to do anything. We can work with them and encourage them. And one of the things that we in the geodetic area of LINZ are able to do from the 1st of July is we can start flagging that and moving back some of those products. So when we're no longer supporting the datums for a cadastral purpose, we're able to make those changes more evident on the website, and even start moving the local datum heights to a back page like we have done with the GD49 horizontal value. So for coming the 1st of July, we can remove some of that supporting information.
Right, I'll just go through the next one. It says, as I understand it, the converted data in NZVD 2016 is not necessarily equalised to the ellipsoidal data. Does that make sense?
I can give an example. I was actually going to touch on that before. So I probably need to share my screen again. Right, assume you can see me. Can you see my screen, Andrew?
Yep, it's coming up.
Okay, so this is an example here that I found when I was putting that example before. So sometimes the LINZ geodetic database has values that are rounded to the nearest centimetre, for example, but they might have an ellipsoidal height that's still 2 millimetres. So if I put these values into the LINZ converter, the online converter with an ellipse orbital height and say I want NZVD 2016 values, these are what I will get. These are the ones that are in the database.
Sorry, I can't see. Sorry, I couldn't see the actual numbers, but I'm assuming they're just rounded off to 2 decimal places.
Okay. I'll zoom in a bit. Can you see that?
Yep.
Yeah, so that one there was obviously rounded. I mean, it's only 3 mils, but it's part of your error budget if you've straight away downgraded it before you start your survey.
And that's based on the orders for the heights that is, so the NZVD 2016 3V heights have been rounded to 2 decimal places to reflect their accuracy in that case.
Okay, I'm not sure whether you all know the answer to this question. Another question: has Auckland City converted their GIS contour information into NZVD 2016?
I'm not aware if they have yet or not. I know that they're definitely planning to, and I'm not sure how far down that project they've gotten.
Right, another one. Person says to Rochelle, still soaking in your comments around local datums and the geoid, is there a good way to relate back to sea level? It seems important in localities such as Hauraki Plains where RLs are typically 1 to 1.5 metres mean sea level, in other words low lying, I guess. Stormwater calculation in low lying areas is an issue. 300 to 400 millimetres is a lot to lose.
So I don't understand that last bit about 300 to 400 being a lot to lose, because the change in datum doesn't change the sea level values. So that's a bit weird. I can't understand that. Do you understand that, Dave?
I think she's referring to your diagram before that you had the difference between the 2 datums is 300 mils.
Yeah, and I think that's one of the things that we haven't been aware of in modern sort of operation, that we've sort of gone to the local datums and we've assumed that they mean sea level and kind of not been aware that they aren't a reflection on mean sea level, which is probably one of the really good things that NZVD 2016 has presented us, is that we can actually address a bit of an elephant in the room, that we aren't actually measuring to mean sea level. Measuring mean sea level, and I've been stinged for too long, sorry, is actually a bit of a struggle. It's very difficult to do. And I see one of the other questions that was about, does LINS keep a record of mean sea level? And we do have a series of tide gauges around the coast where we do monitor mean sea level, and you can find that on the tidal pages of the LINS website. The biggest problem with that is, as we sort of talked about with the datums, is they are only at points around the coastline, and most of them are in harbours, and that only reflects what mean sea level is at that point, at that time, in that location. And the values in the harbour are very different to what's on the open coastline. So it isn't a very good representation of mean sea level much further away from that point. Unfortunately, there isn't a very easy way of determining what sea level is at any point. If you've heard some of my other talks, I would have talked about the JLAS project, joining land and sea, and be coming up with surface conversions between those points. And what we found earlier this year was that we have got some anomalies around the coast where that approach is just not working, and we've going to have to go back onto the drawing board with that. So if you are after local sea level values, it's probably very important to go and measure what that sea level is, rather than relying on calculations between datums. it is a very complex part of our environment.
Another question, just directed to you, Dave, talks about do you have gear for precise levelling, and have you done this for an actual job?
Yes to both, and I think you find that quite a lot of survey firms have, you know, a digital level and a barcoded level stuff as part of their toolkit.
Okay. One question just asked, what is the relationship difference in height between Auckland 1946 Datum and NZVD 2016, which I think Rochelle effectively mentioned in your presentation. Do you want?
So it does vary, and that's part of the point there, and that you were sort of, I can't remember the figures off the top of my head, and I don't have the access to the slides just here, but it was looking at that between that 22 and 30 centimetre, depending about where you are, and it does differ, and that is one of the problems with the Auckland Datum ageing over time, that there's been areas of subsidence, or there's been a mistake in the levelling, which is then propagated out. So it isn't just a one value that you can use consistently across that area, as we had considered in vertical datums past.
Thank you, Rochelle. We've got one comment here about solutions for levelling to a mark with tube, which means putting small stones or sand in the tube, which perhaps get you a little bit closer. But the other option that they mentioned obviously is putting the pole on the edge of the tube, which would give you the right level, I guess. But just a case of, I guess, recording that it's the edge of the tube rather than the centre of the tube. We've got one other question here. Would you have any suggestions on transforming local datums that are not in the conversion tool?
Well, I can answer that. So the best way to reliably convert that data set is to establish a NZVD 2016 on a point within that data set. So presumably it's got some survey marks in it. If you don't have any survey marks, then you probably need to look for something that you can define. Maybe it's a manhole lid or something as your best option, but you probably then need to go and validate that with quite a few checks to be confident that it's the same lid. But once you've established an NZVD 2016 height for a point in your data set, then it's just convert by the difference between the height and whatever datum the legacy data set is to NZVD 2016.
Okay, we've got a few more questions here. Perhaps one for Dave. It says, do you use 3 old marks, as in cadastral surveying, to get agreement with 3 levelling marks? I guess this is to perhaps confirm an origin, perhaps. Are you looking at 3, or do you consider 2 as to be a reliable check, or how do you?
Well, at least 2, obviously. But, you know, you don't always have the luxury of choice. Depends where you are. You know, 3 doesn't hurt, but, you know, you may not have 3 nearby your site. And, you know, 2 at least confirms the relativity between 2 marks.
Another one, any tips on how to detect if a mark used as a benchmark has either come up or down, I guess heaved or subsided, whether it's moved, whether it's moved. Any tips, perhaps? I guess I'll open that up for you, Dave.
Yeah, I mean, visual inspection is not a particularly reliable method, but it might tell you if there's something drastically wrong. But yeah, checking on another benchmark would be the obvious place to start.
And I guess that was the point that you were sort of making there, David, as well, that you can observe any mark in NZVD 2016 and use that GPS measurement straight away to sort of determine if a mark has moved. And if you get even more information, you can sort of put it in that positions PP software to find a better value. So it's really just another one of those tools that you can use. And again, what you're sort of saying, David, is you do need to check it about amongst other marks. Is it that one that's moved, or is it something else that's moved? And it's really getting a better understanding of our vertical data sets in a way that we've sort of done with our horizontal data sets for years. You know, we've really used our heights as an RL value and really not thought about the vectors that go behind it. And a lot of that is just because it was just so difficult to determine heights in the past, that you've, you know, leveling benchmarks, which is several kilometres away, when we've got benchmarks now, or geodetic marks now, which are within a few hundred metres. So we can actually be a lot smarter, if you're allowed to use that word, with how we manage our vertical information.
Right, we are sort of pretty much at the end of our time. We said we'd finish at 1. Even with less speakers, we've managed to fill up the time. So perhaps it's about right to close it off there. I mean, there's a couple of extra questions, but perhaps what we could do is just post some answer online as a way of answering it afterwards. So just to close it off, I'd just like to say that it's my pleasure, on behalf of both the Survey and Spatial New Zealand Cadastral stream and the Positioning and Measurement stream, to thank our 3 presenters. I will say 3 because Carl's done a lot of work. So they are Rochelle Winefield, Carl Wilton and Dave Stewart, and their employers, Linz and Energy Surveys. There's a lot of work that goes into preparing these presentations, and I'm really grateful for their efforts and for their expertise. And I'm sure everyone watching will agree that they've done a great job. So thank you very much, everyone, and we will. And thank you for bearing with a little bit of a broken up or not quite as we anticipated outcome in terms of trying to bring things to you. But we will send through that other presentation, email it through to you. So thank you very much, everyone.